You look up at the digital sign above the airport security line. It says estimated wait 21 minutes. 26 minutes later, you're still taking off your shoes. That sign relies on what statisticians call a point estimate, a single average number calculated from a limited sample of previous travelers. This spreadsheet shows why that single number falls short. The highlighted row in the middle represents one random sample of 10 subjects, giving us an average of 11.1. But this is only one narrow slice of a chaotic reality. Because a sample never perfectly matches the total population, we are left with a mathematical gap called the error of the estimate. Relying on a single point estimate to dictate your schedule, set a budget, or build a bridge is essentially making a highly educated guess. To make reliable predictions about reality, we have to move past rigid numbers and start casting a mathematical net. That net is the confidence interval. It replaces a single guess with a flexible boundary of probability. A confidence interval provides the necessary room for error. Based on our spreadsheet data, we can be 95% confident that the true average lies somewhere between 10.00 and 12.19. Three specific variables control the size of this net. First is sample size. As you gather more data points, the math tightens. Larger samples create narrower, more precise intervals. Second is population variation. If your data points scatter wildly, the formula stretches the interval wider to safely catch the true mean amidst the chaos. The final variable is your level of confidence. Demanding to be 99% sure requires a much wider, less precise net than only needing to be 90% sure. The interval acts as a sliding scale of certainty, balancing the data we possess against the risk we can tolerate. To calculate that interval, data scientists follow a specific decision tree based on what they actually know about the population. Massive samples, usually over 30 items, or populations with a known variance, allow for the use of the z-distribution. But the real world is rarely that clean. Often we are testing a prototype with a tiny sample size and have no idea what the true population variance looks like. This green curve shows the solution, the student's t-distribution, built for small, uncertain samples. Compared to a standard bell curve, it has fatter tails and a flatter peak. The table mathematically expands the interval, compensating for a small sample's mystery. The t-distribution serves as a statistical safety net, preventing us from overestimating our accuracy when information is scarce. This math dictates the physical reality of global manufacturing across the world, such as a factory packing 400-gram tea bags. It is physically impossible to weigh every single bag. Yet, the company must legally guarantee that 400-gram weight to millions of consumers. They solve this by testing a tiny fraction of the run to set strict upper and lower control limits, roughly 385 to 415 grams. If a sample breaches these boundaries, the system triggers a halt. This same mathematical logic guarantees the 50,000-mile tread lifespan of the tires on your car, even though the manufacturer only tested a small fraction. These calculations predict everything from the shelf life of AA batteries to the multi-million-dollar municipal budgets mapped out by city councils. Statistical inference provides a way to quantify our ignorance. By turning a lack of information into a measurable range of probability, we can confidently build, run, and trust the modern world despite never having all the facts.